Okay, great. So it's my great pleasure to introduce our today's speaker, Professor Vincent Wong. Vincent is a professor at the University of British Columbia, Electrical and Computer Engineering, and he's been working on things to do with networking and smart grid for quite a long time. And he has done a lot of work in wireless networks, and he's actually the editor-in-chief of IEEE Transactions on wireless networks. Wireless communication, sorry, which is a big deal anyway, even if it's but great pleasure to have you here in person. Thank you so much for coming, and it's all yours. Thank you.
So thank you, Kisha, for inviting me to come here and give a talk, and happy to give a presentation with all of you. And I do hope that I can learn from some of you later on related to your work as well. So when I give the talk, Kisha actually only has one requirement, and it has something. The talk has to be something to do with sustainability. So I try my best to give a context of how the work is related to the broad area of sustainability. So let me move on to that. So the first slide is related to my research areas. So my research areas are split into two broad areas. The first one is related to wireless communications and networking, and that is my primary research area. And nowadays, my group mainly they work in the area of the sixth generation or the future generation of the wireless networks, which I will spend a fair bit of time in this presentation. In the first part, to explain some of the new techniques, applications related to the 6G networks, which are related to sustainability from my point of view. In my research area, I also mainly work on resource allocation, task offloading, multiple access, integrated sensing and communications. Also, some of my students, they work in the intersection between electrical engineering and computer science as well. In particular, we also look at further learning from the perspective of how we can make it more energy efficient and also resource efficient in terms of how we send the update information from the devices to the access point or to the base station. I also look at traffic reduction as well in the wireless networks. And in the other area related to smart grid and energy systems, over the past 10 years, my students also work in topics related to demand response or demand side management, and that has to do with what if some of the loads are controllable. You can decide when you want to turn on or turn off a particular appliance. Coordinated EV charging, and I believe Kisha also work in this area as well. So that has to do with the scenario that if you have a large number of electric vehicles in the distribution network, but there are constraints related to the capacity of the distribution network as well. So how you can actually decide or coordinate the EV so that they can have the state of charge by the required date, but at the same time, the network is actually not overloaded. Some of my students in the past, they also look at energy trading as well. If we look at the case of, we have different types of DC grid that can interconnect to each other, and how you can do energy trading if you have a large number of PVs or wind turbines or some other renewable resources. And the last topic also related to what I'm going to talk about today is the integration of renewable energy resources in this context. So in the first part of the talk, what I'm going to describe is I'm going to describe some of the new features or the use cases related to the 6G networks. And my goal is to hope that for those of you who work in forest sensing and blockchain in other areas, how the future 6G networks may be applicable to some of the work that you do so that it can further improve or enhance the algorithms that you design. So the first part of the talk is for the future 6G networks, what are the new services and also challenges related to sustainability. So that is so the primary focus here is not just to describe the new applications, but things which I consider to be relevant to the area of sustainability in this context. Nowadays all of us we're in the 5G or the third generation to the fifth generation era. You use your smartphone, then they connect to the 5G networks. But in the research community, we have been working in the direction of the 6G networks since 3 or 4 years ago. And nowadays, in terms of the standardization body, people have also decided what are the new use cases related to the future networks. In wireless communications, there are 2 main standardization bodies. One of them is the International Telecommunication Union, ITU. And in ITU, in the radio communication division, ITUR in particular, for the meeting last month in Geneva, they have decided the new recommendation or the new draft, which is related to the 6G networks. And showing a footnote, that is the framework for the future development of the IMT 2030. So that is equivalent to the 6G networks. The goal is by the time of 2030, network operators will be able to deploy the future 6G networks. So now they have already decided what are the new use cases to be supported in this area. So if you look at the figure here, if we begin with the one in the little triangle at the center, it shows some of the 3 main use cases which are already in the 5th generation networks, but there will be further enhancement here. And that has to do with enhanced mobile broadband. You want to have devices which can support a high data rate, so you can be used to support different types of augmented reality or virtual reality or some other types of streaming applications. There are applications related to ultra reliable low latency communications, URLC, and that has to do with the setting of if you have a large number of IoT devices, Internet of Things devices that may have high reliability requirement and low latency constraint in a factory setting, how you can actually make use of the 5G networks or the future 6G networks to support those applications. And the third major use case is in massive machine type communications. You consider the case that you have a large number of sensors, different types of sensors deployed in a large coverage area. And those sensors, they may need to communicate with the base station or the access point periodically. We look at the specific case that what if in the coverage area, they have a large number of those sensors, but not a small number of them, how you can perform multiple access in this case. And within this triangle, there are some other services which are in this particular area. And 2 of them which I consider to be related to sustainability. One is sensing. So some of you already mentioned you use satellite images, you use different types of sensors as well. In the 6G networks, it is aimed to support different types of sensing applications. And also we are going to use the same frequency band to support both sensing and also communication service. And that has to do with the case that in future 6G networks, besides using the existing current frequency spectrum, we'll make use of the millimeter wave and also terahertz frequency band that can also be used for sensing applications as well. And then in the outer triangle, in the outer circle here, you notice there are a number of keywords from the standard, and one of them is actually sustainability. So sustainability is actually something that people want to consider that as one of the main design criteria for the future 6G networks. And I'm going to elaborate a little bit more in the subsequent slides. So this one is also taken from the ITU new recommendation, and that is related to the capabilities to be supported by the 6G networks. And there are 2 parts here. The lower part related to what are some of the key performance indicators, KPIs, related to the data rate to be supported, latency as well as for services related to localization. What is the granularity that you want to support related to localization? And the very first part, which is showing in green, again, it shows the support of sustainability, as well as some of the AI capabilities as well as the sensing. So many of you, your work includes the use of different types of probabilistic machine learning. But in networking as well, we also look at different types of machine learning techniques for resource allocation and also for network design. So for the existing approaches that we have been using or we are looking at related to sustainability for wireless networks, from the first generation all up to the existing generations, we mainly look at energy efficiency. And energy efficiency is how much power or how much energy required for us to transmit one bit from the device to the base station. And over the past decade, people developed different techniques which try to improve the energy efficiency and also the spectrum efficiency. The summary here is that from the first generation up to the existing generation, we can increase the capacity. That is, for each device that you use, you can get higher bandwidth or higher data throughput or higher bit rate. But at the same time, the energy efficiency has been improved over the past few years. And in the future 6G networks, we want to further increase the energy efficiency as well. Some of the existing techniques that people have used in the existing wireless networks to improve the energy efficiency. One is by using base stations, small cell base stations that instead of having a macro cell that has a coverage area of say 1 kilometer, we deploy a large number of small cells which has a coverage area between say 100 meters or 200 meters. The distance between the device and the base station has been reduced, so the transmit power has been reduced as well. And we also make use of different types of power control to mitigate the interference, while the base stations can make use of the same frequency spectrum for transmission. There are other devices that can perform energy harvesting capabilities.
Just a quick question. I mean, look, from the previous slide also, it just said, it looks like the way achieving all these very high performance goals is to increase the number of space stations dramatically, right? By a factor of 10 or 100, right? Because that's the only way you can get very high data rates and low latency, given the underlying system.
That's one approach. The other approach is actually using a high frequency band.
Okay.
So that is also making more resources for the application spectrum.
Okay. Then the reason I said because we have more base stations, then of course you have more embedded energy in the system itself, in the network itself. Because you manufacture 100 times more devices and deploy them and power them. Right? That's correct. But there have been studies that I didn't show it here. Is that it shows that even though you increase the number of base stations, but overall the energy efficiency has been improved quite a bit. Yeah. Okay. Great. Thank you. So apart from energy harvesting devices, there are some sensors that can actually harvest the solar energy for quite some time. Once it has collected sufficient energy, then it can transmit the corresponding data to the corresponding sink or to the base station. And at the same time, they are also using techniques of backscatter communications. So the base station will send data, and the device can harvest the energy and then transmit the acknowledgement of the information back to the base station as well. So one typical short-range application is by using RFID, but there are also other techniques in the backscatter communications area that can provide a longer transmission range. The next slide actually taken from a magazine article by ISAC from Virginia Tech, and this one shows the applications, driving trends, and also enabling technologies as well. And in the first part, you notice that some of the driving applications are also related to some of you guys that are working on, including blockchain or smart contract, which is shown in the top right corner here. Different types of sensing applications. And in the middle part, we make use of the machine learning or the AI techniques to control the networks. And we also make use of different techniques by sharing the same spectrum and by controlling communication, sensing, and localization within one particular domain as well, which is called the convergence in this context. We make use of the high frequency band so that you can have a high data rate. But apart from that, there will be other technologies that make use of instead of using terrestrial networks for base stations and access points in a 6G networks, it will also be deployed of the
satellite communications by having a global coverage. And there's a trend that there are now companies that deploy very low Earth orbit satellites over the world, so that in areas that may not have cellular coverage, then a device can switch to the satellite link for efficient communications. There are also works that are related to the use of drones and also high altitude platform stations helps as well to actually provide temporary coverage within a certain area if there's not enough bandwidth in that particular case.
Sorry, I need to, there's so many interesting things. Three questions, quick one. First one is wireless brain-computer interaction. Is that really a thing? I mean,
yes, there are already companies that study the case that there may be embedded devices close to the brain or in parts of the body that can actually collect sensitive information. And people look at the case of using those haptic devices as well that can actually, and those devices typically they require a very short latency so that you can receive the corresponding haptics feedback information. And that is one of the use cases in the ultra low latency communications area.
Okay, that's amazing. And then it's an end of the smartphone era. What does that mean?
And of these is one is right now the smartphone nowadays we mainly use that for communications, entertainment, streaming as well. But people look at the smartphone in future is a little bit like those Star Trek devices that has different types of sensors that it can do some diagnostics as well and also collect a lot of sensory information. Nowadays we use smartwatch to do that, but in future there will be more capabilities in the smartphone that can provide those information.
Okay, and the last thing that we talked about is a low Earth orbit satellite. You can switch from base station to satellite. Is it on the same GSM bands and the same? Will the base station be? Sorry, will the handset need to be modified to talk to satellites? Or
it will be a different frequency band. And right now there are already some companies already have some prototypes that can actually have this kind of capabilities already. And the main question is whether or not there will be wide deployment in future.
So the reason I ask is, if you have something in the forest you want to measure and you want to send back to analysis, right now you're basically disconnected operation. Everything is done remotely. But if you had access to low latency communication, lowish latency communication from the field, that completely changes many of these problems actually.
Yeah.
And so it would be very interesting to see whether these systems are actually going to be deployed and made available.
Yes, in communications area, we mainly look at the case that if you have a large number of those very low orbit satellites, that the device it will no longer be the stationary satellite. We look at beamforming, and we also look at researchers look at beamforming and also look at the handoff in different time. Right. But the satellite part will for sure be one of the features in the
something like Starlink, but a cheaper one,
Yes.
Great, thank you.
I had two questions. One of them goes back to something you said before. I've done some work with millimeter wave technology on cell phones, and you mentioned integrated sensing and communication on those wavelengths. Can you explain what you meant by that?
I have one slide later on to show that, but I don't have any questions to show that. And I guess this is actually one I will use this one as an example to show that. In radar as an example, for a long time, radar system and communication systems, there are two separate systems. They use different frequency bands, and in the communications aspect, the waveform you use for radar and the waveform you use for communication, they're totally different. And nowadays, by using millimeter wave frequency band and also terahertz frequency band, researchers are looking at using different types of waveform that can perform communication and sensing in this case. And in this example, it's taken from my student's paper, is the base station will transmit the ISAC signal, which is for communications. And then the reflected signals will actually be used for tracking of the vehicles as well. So this is one example. There are other examples that can be used for communications and also tracking of other objects as well, and also can be used for localization. So ISAC in this case is that we can have one system that can perform both sensing and also for communications, so that you can reduce the cost of having two systems. You can have better spectrum efficiency because you can make good use of the spectrum as well. And at the same time, it can further drive down the cost. And in the last bullet here, I show one in blue color, it's called sensing as a service. Is what people consider is in the future 6G networks, if the mobile service providers, apart from deploying base stations over the city or different parts, they also either the base station have sensing capabilities or they deploy sensors which are owned and monitored and managed by the mobile service providers. So in this case, sensing as a service means that the customer can inform the mobile service operator saying that at a certain time, say from Monday, from 6 o'clock to say 9 o'clock, I want to collect particular information, say pollution or some other information within a particular area. So the mobile service operator can actually perform that task on behalf of the customer, instead of having the customer deploy their own sensors in this case. So that is similar to some of the services in cloud computing in the house. In the 6G networks, there will be two keywords shown here. One is the AI for network here, the other one is for network for AI. AI for network here means that for the wireless networks, there will be different types of algorithms which will be deployed mainly for resource allocation and control of the wireless networks. So in this case, instead of using the existing approach, which can be say simple heuristics or based on some optimization techniques, so they will be using machine learning to collect the data and then decide how much resources you want to allocate at different base stations in an appropriate manner. So that is what we mean by AI for network. The second part of network for AI is actually the other way around. Is people are now looking at how you can come up with a new network architecture in the wireless network domain that can support different types of AI applications. And in particular, we will look at the case of different types of distributed AI applications, including, say, federated learning or different types of large language models or decentralized large language models, machine learning applications in future. And this part is also related to sustainability as well. And we do have a lot of right now. That is also one of the challenge in this case. Let me in the next two slides. Let me elaborate a little bit more. Federated learning is a hot topic in machine learning community, both in academia and industry as well. There are many top machine learning conferences which have many sessions in federated learning. In the electrical engineering or communications area, we look at federated learning from a different perspective. In computer science, people look at issues related to, say, device heterogeneity. They also look at things related to data heterogeneities. What if different devices have different types of data, local data sets? What if different devices have different capabilities in terms of the CPU computational capability? So those are the works that what people look at in computer science. In electrical engineering, we look at other aspects related to how we can make use of the wireless networks in a more efficient manner to send those gradient updates or those models to the network in an appropriate manner. So we look at, say, over-the-air computation and also other techniques that can allow us to actually have a more efficient transmission of make use of the network to support distributed learning applications. This slide is actually taken from one of the keynote presentation by Viren Debak from at IEEE keynote, and this one is related to what happens in the future. There will be different types of sensors. So in this slide here, in the first part, the keywords that I show is here is a multi-modal wireless data. So you have different types of sensors that can allow you to collect information related to radio signals. It can be related to sound, light, and different types of sensors as well, which are collected by the base station. And what is actually looking on right now is that people also look at large language models, say ChatGPT and many different variations. What is the impact in the network design? So people look at two parts related to AI for network has to do with can we make use of some of those large language models to come up with new algorithms to control the network? So that is one part. The other part, which is actually more important, is if there are more different companies which deploy those large language models, and at the same time, there are distributed large language models applications in that case, but you need to do the training, and at the same time, every once in a while, you need to send those models, send those updates to other devices. But the problem here at this time is that those updates, the file size will be significantly large, very large. So the question is, what are the techniques that we can use to actually send those updates in an efficient manner? In terms of the bandwidth, in terms of the energy resources that we use as well. People envision that there will be a lot of those hierarchical updating and aggregation. So instead of the base station, there will be some mobile edge computing servers in between, and there will be some aggregations as well. And also people will make use of typical approaches using model compression and quantization as well. But then those techniques are good, but they may not be sufficient if you have a large number of those applications, AI applications. So that has to do with the question is in future, which is an open question, is at the end of the day, we can make use of the wireless networks that can support new services, including digital twin, smart city, different types of environmental applications as well. But at the same time, to control and monitor the network, at the end of the day, do we actually need to use more energy than before? So that is actually one of the open issues that people try to tackle, and they want to look at ways that can support all those applications. But at the same time, the network still have to be energy efficient. We may be able to learn techniques from what people did in the past, but at the same time, there are new challenges. One other challenge is that I'll just briefly mention here is in, say, smart grid or energy system area, a lot of work has been done in data center. Data center, you call data centers, but at the same time, the people strategically decide where they want to have the data center, they want to use renewable resources. So that you can have the electricity bill to be relatively low. But then wireless network is actually very difficult because you want to deploy base stations almost everywhere. And you also need those controllers in different locations as well. So, so people are now looking at what are the better ways to actually have energy efficient network design. So that's why in future 6G networks, sustainability is actually one of the key issues for the design. So in the first part of my talk, some of the messages that I want to provide for you guys who are experts in your own domains is that sustainability is indeed an important design criteria for the future networks. And 6G networks in future can provide different types of sensing services and can also collect different types of sensing data. Instead of using this the wireless networks as a pipe or for the transport architecture, it can also be used to do some computation, control, and so aggregation as well. And 6G networks will be important for applications, in particular for the different types of digital twin in industrial setting, building management as well, and also related to environmental monitoring. But then one of the open issues is that if we have a large number of those distributed machine learning applications, we do need to have energy efficient algorithms that can have a high energy efficiency, but at the same time support all those applications with different types of guarantees. So that's what I want to provide in the first part. And then I move on to my second part. And I want to just use one linkage or bridge to bridge my first part and the second part is, the second part is essentially what I want to do related to energy system or power system. And the linkage that I want to use is the use of machine learning can be used, different techniques of machine learning can be used to control wireless networks. And it can also be used to control power systems, energy system as well. And this is one example that I'm going to present by using machine learning technique of how we can study a problem related to distribution network reconfiguration. And this is not a new problem, but it is still an open problem, simply because nowadays there are renewable energy sources which are integrated into the distribution network. So this is the joint work with my former postdoc, Shahab, who is now working in his own startup company, and my colleague, Christine Chan, who is an expert in power system area. So the first part of the talk, the second part of the talk is first introduce what is the distribution network reconfiguration problem here. And I try to make use of this figure to give you an idea. And my apology that the figures are relatively small. So this is a typical distribution network. So electricity goes from the transmission network to the distribution network here. There are a number of buses, or you can simply consider as a nodes. And those buses are connected to either the buildings or to the residential areas. On the left-hand side, there's one substation bus, which is connected to the transmission system. And these buses here, some of them are connected to the load, and you also notice that some of them are connected to the PV panels, and also some of them are connected to the wind turbines as well. And this distribution network, the lines have a fixed capacity. And then what you're not showing here properly is that there are also a number of switches as well, which can open and close. Some of them are called the sectional switch. Some of them are called the timeline switch, which are not showing here properly. But what I want to show is that these switches can be open and closed. And in that case, the topology of the distribution network can actually can be changed every 10 minutes or every 15 minutes. So because you can open and close the switch, so in this case, you have a set of binary variables. Even in this setting here, the number of feasible configurations is actually very large. So it is not feasible to use, say, enumeration to actually figure out what is the best topology. And this type of dynamic distribution network reconfiguration is important during the times that if some of the loads actually have variable demand and the PV may generate more energy than before. And what happened? There's also a transmission line faded as well. So this is actually the setting that we want to look at is how we can come up with a good algorithm that can decide whether or not a particular switch should be open or closed in a distribution setting. And how it is related to sustainability is that we envision that there will be more PV panels to be deployed in different households, and at the same time, there will be more different types of variable loads, which say EV charging as an example. So instead of looking at coordinated EV charging, this time we look at the case that what if you can also control the status of the switches. So you can actually, instead of upgrading the distribution network, you can make use of the distribution network to support more load and in a flexible manner. So typically, the distribution network reconfiguration problem is formulated as a mixed integer optimization problem. Mixed integer has to do with a large number of binary variables that you can close and open a switch. We want the objective here is to minimize the loss, and the loss including the loss of the transmission lines, which are the resistance multiplied by the square of the voltage function.
In this network, is there directionality? Like,
Yeah.
okay, so the switches can open, but they can't change the directions.
the direction can also change. In the past, before in the old days, without the use of without the PV, it is a radio network, the substation bus, and then the power will simply electricity will go down. But nowadays, with the use of PV, power can also go up as well. But there's a set of constraints which are the power balance flows equations that you need to balance the all the power.
So part of the things you're allowed to switch in the distribution network reconfiguration problem are directionality as well as just open and close.
Open and close, and the constraint here itself will figure it out what's the corresponding direction.
I see, okay.
So in the optimization problem, it has a number of individual local objectives, including minimize the net losses or the power losses. So it's the resistance multiplied by the square of the voltage. You cannot open and close the switch in each time slot because you want to mitigate the corresponding wear and tear issue. So people typically they look at the case that maybe you can decide whether you want to open or close the particular switch. Maybe say every 2 time slots or every 5 time slots. It is possible that at a certain time you may not have enough resources or electricity to support all the loads. So that there will be a case that some of the loads will be disconnected for a short period of time. So there's a cost for the load interruption. And if you do not have enough load, you may also be able to turn on some backup generators. It takes time to turn it off, takes time to turn it down as well. And then also, so we need to consider the cost and the operation constraints. The operation constraints in this case here, including the constraints related to the temporal constraints that you can only, the number of times that you can turn on or turn off within a certain time interval is fixed. There's from one time slot to another time slot. If you want to use a backup diesel generator, you can only increase the energy output by a certain rate. So that is a ramp up constraint. And when you turn it down, you can only reduce by a certain rate. That is a ramp down constraint as well. And there's also another constraint which is important, is the AC power flow constraint. And that has to do with the fact that you want to make sure that the network itself essentially can balance all the corresponding load in appropriate manner. So in this case, the whole problem is a mixed integer nonlinear optimization problem. This problem has been studied by different researchers over the past few years. And some of them, they also make use of the machine learning techniques. But many of them, they only make an approximation about the power flow equations. They assume either linear power flow equations, or they make some kind of approximations as well, which may not work appropriately if you want to consider the actual practical systems which have the actual power flow constraints. So in our work, what we want to do is we want to study by using the reinforcement learning technique. We formulate the problem as a markup decision process, and then we use DRL with anti-critic to solve the corresponding distribution network reconfiguration problem. We are going to, I will show you the DNN for the anti-critic later on. In our work, we consider AC power flow constraints and how we can actually obtain the corresponding policy to decide whether or not I want to turn on or turn off the corresponding switch. And later, and I'll also show you the results related to 119 bus distribution system and how the algorithm perform when we consider a much larger distribution system with a finite number of substation buses.
We have about 15 minutes. I should want, yeah.
Okay.
Yeah, you're inside 15 or 30%.
Okay, sure. Okay. So what I'm going to do is I will just describe the key parts of what I want to show is in the system model with a number of substation buses, and also a bus can also be either PV, can be a diesel generator. We make decision in a time slot by time slot basis. As an example, the time slot can be equal to 15 minutes. We have a number of binary variables in this case, and the binary variables corresponds to whether or not you want to open or close a particular switch. The corresponding variables, because you can only, once you turn on a switch, you cannot turn it off right away. You can need to wait for a certain time, so that we need to keep track of the history. So we have these auxiliary variables to decide whether or not the status of the switch was open or closed before in a fixed number of time slots before. We also need to introduce binary variables to decide whether you want to serve a particular load in a particular bus, and whether or not you want to use the backup generator at a particular bus or not. So we have a set of these binary and auxiliary variables. Related to the AC power flow, we have a set of variables related to, these are all continuous variables related to the active power flow and also the reactive power flow as well. And the active power flow is the actual energy or the power which actually used to serve the corresponding load. So those are the useful power in this context. In the distribution network with configuration problem, if we want to formulate the problem, it's a Markov decision process. The system state in the current time slot T, they include some of the information is what are the statuses of the switches at the end of the previous time slot T-1, the status of the backup generator in the previous time slot, the active and reactive power components of the load and renewable generation, as well as the corresponding upper limit of the substation bus as well. So these are some of the notations related to the system state, related to what happened in the previous time slot. And the corresponding constraints in the MDP include the following. I didn't include the set of equations here. I just include the corresponding constraint. Because we look at a distribution network, we have a set of spanning tree constraint in this case here. So the root corresponds to the substation bus, and the distributed network in this case has a radial topology, and all the buses have to be connected. Because the switch can actually be open or closed within certain consecutive time slots, so we have these intertemporal constraints that we want to consider. If we want to make use of the diesel generator, there's a ramp up and ramp down constraint for that particular bus. And we also have the constraints related to the power flow and the active and reactive components as well. So the action vector that we want to decide in a particular time slot is actually shown here. And in brief, the action vector can be divided into two parts. One is related to the binary decision variables. The other one corresponds to the continuous decision variables that we want to consider. And the cost function include the losses in the network due to the resistance in different lines, the switching cost, the use of the backup generator. If we are not able to serve a particular load, there will be a penalty. There will be a cost incurred as well. And so that is the corresponding cost function. So we want to determine the policy so that we want to minimize the total cost. And the way we look at that is, instead of formulating that as a discounted Markov decision process, we look at the average cost criteria. So in this case, we have this typical way to formulate the average cost MDP in this setting here. The action has binary variables and continuous variables. The feasible space that we want to consider has binary variables, and we have constraints that are actually non-convex because of the AC power flow conditions. So the way we want to solve the problem is that we are going to decouple the problem into two parts. One is we first solve the problem by determining the corresponding binary variables, and then we solve the corresponding ACOPF problem to determine the corresponding feasible flow. So this is actually the algorithm that we come up with here to solve the corresponding problem. So the way it works is that in the lower part, we have the state information that comes in. And in the first part that we have here, because we have the binaries and also the continuous parts, we first determine the relaxed DNR by relax those binary terms, and then we determine the corresponding output of the corresponding setting, and that is used as an input to the corresponding actor DNN. The actor DNN in this case is to use to determine the corresponding policy related to the corresponding binary decision vectors. So this is actually make use of the transformer network for the actor DNN. The output, which is shown here, corresponds to the whether or not a particular switch should be on or off, whether or not the corresponding diesel generator should be on and off, and whether we can serve a particular load or not. And once we have the results for the corresponding binary variables, we feed in to the corresponding penalized OPF showing in here. The way we need to look at this one is that we notice that it is possible that based on the binary vectors that we obtain, it may not be a feasible solution to the original OPF. So we need to include a barrier term or barrier function or penalty term into the corresponding OPF in order to determine the corresponding continuous variables, which are the power flow variables. And then the output corresponds to the power flow. We fit it to this part here, which allows us to determine the corresponding TD error. So the critic in this case, we use a multi-layer perceptron to determine the corresponding relative value function. And the TD error that is shown here allows us to actually update the corresponding network parameters for the actor network and also for the corresponding critic network as well.
Yeah, sorry, just a really quick one while you're on the slide. Can you give us a feel for the parameter space that these evaluation networks are operating over? You know, sort of how many parameters are going into your system, whether it's the physical instantiations or there are more hidden parameters that are undisclosed. I'm just trying to get a feel for how big the network is and therefore how fast it can operate.
Let me try to
Billions,
is
thousands.
in a range of thousands in this case.
So that's great because it means you can go very fast. What guarantees that you're not going to keep circulating around without a converged solution in your bottom loop?
We don't have a theoretical guarantee, but we have one I can show. We later on will show the results. We show that it always converges this case. Yeah. Good. Thank you. I have 8 minutes, right?
Yes, okay. A few than that.
I should have. So in this case, I will just show you the results. The first part that I'm going to look at is the same topology that I showed you earlier. We consider 119 bus feeder, and many of these many parts are open and closed. So you have a large number of binary variables in this case. And we consider two types of loads. One is related to the residential, one is related to the commercial load. So that is related to the load at different time of the day for residential and also commercial. So the first part that is showing here is a TD error. When we increase the number of, or we train it about for 7,000 iterations, and eventually the TD error approaches 0. So the algorithm converge, and the expected average cost that we obtain in this particular example here is about 1,500. So that is used to show that indeed the algorithm converge in this setting. And then the second part that I'm going to show is that because we did not do any prediction and we do not do any forecasting, so we compare with another algorithm that actually do forecasting. And the results shown here is that the red line is actually our proposed algorithm based on deep reinforcement learning, the one which is shown in the red color here. And we compare with another one which is based on mixed integer second order programming by using some approximation. If the x-axis corresponds to the forecast window, if you look at the case that if there's a genie that can forecast what will be the load and what will be the PV generation for the next 2 days, 48 hours, a post algorithm, of course, cannot be the genie, but then the gap is about 8%. But if you compare with another genie that can only do the forecast of about say 14 hours, it shows that our proposed algorithm actually has the same performance as those that can actually perform a good prediction within 14 hours. And our proposed scheme actually has a better cost, a lower cost in this case, compared to the algorithm that only do prediction for a short number of hours, say 4 hours, or even do not do prediction as well. So this one shows that by using the reinforcement learning approach, we do not learn the state transition probability distribution, but then it can have a good performance compared to those that have complete information about what's going on in future. We also compare, look at the results for the case that what happened at in certain number of days that the load is actually more than the energy that can be supplied by the transmission network. Then we need to turn on the backup diesel generator, and even the PV generations is actually not enough. So in the bottom line here, it shows 4 curves. The one which is the red color is the lower bound. That is the DNR with complete information. Complete information here means that you have a complete forecast. You know what's going on in the next 10 days with complete information. The blue one is the one that we propose, and the other 2 corresponds to 2 other heuristics. One from reference 20, the other one is a heuristic based on the Rudy algorithm. So this one shows that our proposed algorithm actually has close performance compared to the case that has complete information in this context. We also compare the case with a large number of buses. So this one shows that instead of using 119, we interconnect those 190 buses together to form larger distribution networks. So in this case, instead of having one substation bus, we have multiple substation bus. And this one shows that even in the large test systems, it takes more iteration for the algorithm to converge, but eventually our algorithm actually converge. And this one shows the corresponding expected cost in this setting. So this one shows that the proposed algorithm also works in the large test systems in this context. So to summarize the second part, we look at the distribution network reconfiguration problem from the perspective that we want to consider the AC power flow equations. We use an adequate approach to actually come up with the algorithm, and the proposed algorithm shows that it can lead to a lower cost compared to some of the techniques proposed in the literature, and compare with the case that there's a genie that can predict what's going on in the long time horizon. The gap between our proposed scheme and one for complete information is relatively small. So for future work, we'll look at the case that what if the distribution network have different buses that also have energy storage, and also we'll look at the case of decentralized approach to control the network. So that's the end of my second.
Great, thank you very much.
So perhaps I misunderstood quite what you meant by bus in this context, because 3,570 buses can maybe enthusiastic. So did you study the other direction of travel, which is okay, the background. The background is there is only one bus in the UK. The whole nation runs on a single bus. And so I'm kind of curious, at least the supergrid does. And so I'm kind of curious what the implications are here, because it's the other direction of optimization. It's optimizing one extremely wide geographic area, which has some constraints there, but with many, many, many generation sources. Obviously some very big ones, but many, many small ones. And I was wondering, that sounds like it might be perhaps reasonably something that's not actually a state space you can work in.
That's correct. The first part of the talk, the reason why we look at one bus in the rhythm topology is to do with the fact that in the penalized part, we make use of the previous work by Stephen Lowe on the OPF part in ACU, and that one shows that in that context, Only if the topology is the radial network, then the optimization gap is actually equal to 0 in that case. So that's why in the first part, we look at the case that there's only one substation bus. But the approach that we look at here can also be extended to the case of having multiple substation bus, and even we.
So this, sorry, this 3,500 or any of these actually,
Yeah.
you're talking about a single substation.
Multiple.
So what's the structural architecture that we're defining? Was it the one that you had in the picture, where effectively it's a linear with.
I don't have a figure here. It's somehow we make use of the original 190 buses and we interconnect them in specific locations to create this particular test systems. And we for that particular test systems, we actually make use of take a look at another paper and look at how they create those kind of logic test systems as a reference for us to actually come up with our own topology.
Okay. Any other questions? Okay, maybe I can just ask a quick thing. So, I mean, in DRL, I assume in real life, the DRL will be doing all the actual subsystem, right? So all the training periods you have, the system is not working optimally. In fact, it may be operating very badly. How do you deal with that in real life? I mean, it might take several days even before you get.
I think for now, we need to look at it. I think in practical system, we have to do this kind of training offline first,
Right.
and then let it work. And there's also in power system area, people also make use of technique called safe DRL. There are also quite a lot of papers in that area. So if you have those. If you use a safe DRL setting, then you have some barrier thing constraints, then you can guarantee that during the training process, you will never actually violate any of those constraints.
Okay, so you take your action space and protect ground to save subspace.
That's one way to do that. Yeah.
Okay, great. Thank you very much. Okay, in the interest of time, let's have this again. And that brings us to the end of the talk. Thank you. And okay, well, I'm afraid we have two problems. One is I'm out of time. I need to go to the meeting. And second, you have a lot of food left. The first, you should help yourself. Or you told me it's not something else. And second,